Hi, everyone, and welcome. Can you hear me? Just checking. Sound okay? Excellent, thank you very much. Before we dive into data productivity at scale, let me share a few words about myself and my background. So my name is Yaroslav. I'm a co-founder and chief architect at Tabika Data. I've been leading the development of SQLMesh, the open source data transformation and modeling tool. Raise your hand if you heard about SQLMesh before. All right, a few people. Nice, very good. So hopefully by the end of the talk, there will be more hands. So before that, I have over a decade of experience leading various data and ML infrastructure initiatives. And most recently, I did this at companies like Netflix and Apple. Now you know who I am, but why am I here today? Well, I'm here today because I believe that we, data practitioners, face a series of challenges that have long been addressed by our fellow software developers. For example, how do we test our data pipeline changes today? If we ask a software developer how do they test their web apps or backend service, they would tell you that, among other things, they heavily rely on environments. They have local environments, testing environments, staging environments. They spin them up, they tear them down as much as they like. Why can't we have nice things? Well, we can't have nice things because, as it turns out, creating testing environments for data is extremely hard. How do we even create testing environments for data? Do we ask a data infra team to provision a new schema or database instance? How many environments do we need? Is it one per user? Is it shared between multiple users? How do we preserve isolation between different changes that we test? Okay, assuming we figure the creation part out, how do we populate new environments with data? Do we maybe sample production data or generate some synthetic data? Is it really representative of the data that we're going to face in production? Maybe should we maybe copy production data? Well, that's certainly better, but not very runtime efficient. As a result of these challenges, the development iterations are slow. We need to wait a really long time for the computation to finish. Alternatively, we resort to testing only a subset of our changes, leading to catastrophic consequences for downstream pipeline and consumers in production. Or we test using incomplete or inaccurate data with more or less the same outcome. Furthermore, the production deployments are very ad hoc and error-prone. For example, when I was at Netflix, and Netflix has a very strong data team, I would run outer table statements manually against production tables in order to apply my changes in prod. And I assure you, it was an extremely stressful experience, requiring me to double and triple check every change I made. So how do we move away from this kind of flow? How do we make sure that the changes we deploy in production do not leave it in a broken or partial state? How do we quickly revert our changes if such a situation did occur despite our best efforts? Long story short, all of these challenges make us a lot less productive than we could have been. Now, on the topic of scale, all the challenges that I described, although universal, become even more pronounced at scale. And when I say scale, I bet you're thinking something like this. But the size of your data is not the only measure of scale. Another measure of scale that is a lot more relevant to what I'll be talking about is organizational scale or organizational complexity. Remember the last time you tried to explain the lineage of your data to a colleague or a stakeholder? This complexity is real, and it can be measured by the number of people who build, maintain, and use analytical pipelines in your organization, or even by the sheer number of those pipelines. So I'm here to offer you 3 pillars of data productivity. The first pillar, data versioning, to maintain a historical record of changes that you make, and to be able to switch between different states of data freely. Second pillar, virtual data environments, to create isolated environments for development, populated with up-to-date representative data in a fast and cost-efficient manner. Automatic data contracts. I bet you hear about data contracts a lot these days. But what I mean here is the ability to assess impact of your changes and identify breaking changes. And what makes them automatic is the fact that you don't need to write any extra YAML. So, and these 3 pillars support fast, safe, and cost-efficient development process, the nirvana state that we all strive for. So now we're going to build this little partner together, brick by brick. Let's go. So when talking about the first pillar, data versioning, I don't mean versioning of physical objects in your data warehouse or lakehouse. Iceberg, Delta Lake already solved this for us. What I mean is more high level than that, and I'm going to refer to this high level concept as model. I'm going to use model as a term a lot throughout this talk, so I need to address it first. And so if you come in from DBT background, you already know what model is. But for the rest of you, when I say model, I mean transformation process, basically T in ETL. One way to define transformation is using a SQL query. So here's a simple transformation which projects columns A and B from some source, while at the same time filtering out rows that are less than or equal to 0. Now, the transformation logic, the SQL query alone, is not enough for a model to be a model. For a model to be a model, there got to be some execution process, something that runs the transformation, as well as associated data object in your lakehouse, like a table or a view where the result of transformations are stored. To recap, for a model to be a model, there's got to be a transformation logic defined as, for example, as a SQL query, some execution process that evaluates the query, and the associated data object. So Git already takes care of versioning the left-hand side of the arrow. Iceberg already takes care of versioning the right-hand side of the arrow. Our goal is to version both sides of the arrow simultaneously and map the two versions with each other. And why we need that will become clear later in this talk. So now we can take this model, like this transformation logic, this SQL query, along with like other attributes that can define the model, compute its fingerprint, which is a fancy name for a hash of its attributes, excluding stuff like code comments, code formatting, and other things that have no functional impact whatsoever on the data outcome. We can put these two things together and call it a model snapshot. And fingerprint essentially serves a purpose of a unique identifier of the transformation logic, like a specific version of the transformation logic. So we can now put this model snapshot into a state, basically record it for prosperity. So please note, if you're coming from dbt world, it has nothing to do with dbt snapshot. It's a completely orthogonal concept. So now we have a historical record of changes we made to the transformation logic itself. But how do these various versions map to data objects in our lakehouse or data warehouse? Well, the mapping is surprisingly simple. Every time you create a new version, a new object or a view gets created for it in your data warehouse as well. So for example, if I were to change model A, update its SQL, for example, a new snapshot will get created for it, and a new table will get created for it as well. So to recap, model fingerprint uniquely identifies a specific version of a model. Model's transformation logic, along with its dependencies and attributes, get packaged into these self-contained snapshots, which are immutable. Each snapshot gets associated with its own table or a view in the data warehouse. So put together, these components allow us to to preserve the history of model changes, not just at the definition level, but at the data level as well. So now we need to figure out how to access these various snapshot tables and how to pick which table version to access at any given point in time. So for this, we're gonna separate our data warehouse into two layers, physical layer and virtual layer. So please know that no such layers actually exist anywhere. This is just like a mental construct that helps us reason about various objects that we're gonna introduce here. So we already know what to put into the physical layer. Unfortunately, there is a closed capture right over it. But in the physical layer, these are the version tables that we just talked about. So nothing new here. What about the virtual layer? So in the virtual layer, we create a bunch of views which point at various snapshot tables using simple select star from query. And these views, in turn, have well-defined names that are known to downstream consumers and users and which are used to actually access the underlying data. So we introduce this level of interaction with views serving the purpose of pointers to various version tables. But why? Why do we need such interaction? So let's look at the following example. So let's take the views that we just created, put them in a box, and call this box production environment. Now, if we want to make some changes, we need to create a development environment first. So we're going to create a new set of views with slightly modified names. For example, we can add an environment name as a suffix to the schema portion of the model name. And we call this new set of views development environment. So now if I were to make changes to model A, for example, a new snapshot will get created for it, as well as a new new table gets created for it as well in the physical layer. Next, we're going to update the view in the development box to point at this new version table. Note that the view in the production box remain completely unchanged. We preserve the isolation property of our testing environment. Also note that model B hasn't changed at all. So we can conclude that we can reuse the model B snapshot table as well as the data associated with it as is without computing it at all. Now, once we are done iterating on model A, we can deploy the change back to production. And for this, we just update the view in the production box to point at this new snapshot table. And this change, this update, takes place almost instantaneously, or the time it takes to replace the view. Also note that the underlying data for the snapshot table can be evaluated and validated long before we swap the view, which means that downstream consumers and users are never exposed to partial or straight wrong data. So I can already see some skeptical looks in the audience. You're probably thinking, Yaroslav, rebuilding tables from scratch is nice and all, but what if? What if the table is too large and costly to rebuild? What if the model logic is not idempotent, meaning that running the same query multiple times yields different results? What if the historical data is not available upstream? Well, unfortunately, this is a lightning talk. I can't cover it all. But to tease you a little bit, we take care of this with a concept called forward-only change, which means that changes are applied going forward using the existing version table as opposed to rebuilding it from scratch. At the same time, we allow to compute a limited preview in the development environment. Obviously, the trade-off is that if you want to roll back a change, it's no longer as simple as just swapping the pointer. You actually need to run the explicit data restatement process. Let's recap. So the data warehouse gets divided into two layers, physical layer and virtual layer. So the physical layer is where version snapshot tables reside. Virtual layer consists of views with well-defined names which point at various snapshot tables and which are used by downstream consumers to access underlying data. Environments are just collections of views. Using them is cheap, they are fast to create, and they are populated with up-to-date representative data at all times. So the next pillar, the automatic data contracts, heavily relies on our ability to semantically understand the transformation logic. But what does semantic understanding even mean? So remember this query from the first slides? We can parse this query into a tree-like structure that is called abstract syntax tree, or AST for short. In this form, we can reason about the query, we can analyze it, we can optimize it, get column-level lineage, and other cool things. So one such cool thing I'm about to show you. Let's imagine we changed the original query and we added projection D to it. So now we can conclude by looking at the tree-like representation that the change is non-breaking unless downstream models use select star query, which we shouldn't do ideally. So we can conclude that the change is non-breaking, which means that we only need to recompute the transformations that we modified without touching anything else. We don't need to compute downstream because we know that there is no functional impact, and we don't need to compute upstream because we know that it hasn't changed. Now, what about the breaking change? Instead of adding a new projection, we actually change the threshold for the filter. So now we can conclude that the change is breaking because the cardinality of the table changed. That means we do need to recompute the downstream dependencies in order to correctly preview and reflect our changes. Okay, let's recap. Semantic understanding, or understanding the meaning of a change, leads to our ability to categorize changes as breaking or non-breaking. Users always know what kind of impact their changes will have before a single execution takes place. Additionally, this leads to a drastically reduced computation for non-breaking changes, leading to users being encouraged to make fewer breaking changes. Okay, finally, we are ready to finish this, the construction of this little Parthenon. Data versioning ensures that we can easily go back and forth between different changes we made. It unlocks paths to virtual data environments, which are further enhanced by automatic data contracts. Virtual data environments are a cost-efficient way for users to get a complete and accurate preview of their changes using up-to-date representative data, while simultaneously ensuring safe deployments to production. Automatic data contracts ensures fast feedback loop by assessing the impact of a change before a single execution takes place, as well as drastically reduce necessary computation for non-breaking changes. Finally, if we put this together, we get fast, safe, and cost-efficient development process. So if all of this sounded a little too abstract, no worries, I'm about to show you how these ideas work in practice on the example of SQLMesh. And to recap, SQLMesh is an open source data transformation and modeling tool. Everything in there defined either as pure SQL or pure Python, no Jinja involved. You don't need to line a single line of Jinja code. Even something like macro can be expressed as pure Python functions, which are subsequently called from SQL. It comes with batteries included. Things like interval tracking, unit testing, CI/CD, Airflow integration, all the things that a modern, mature data transformation framework should have these days. It's backward compatible with dbt, which means that you can use it as a drop-in replacement for your existing dbt project. But more importantly, it brings 3 pillars of data productivity to life. Right. So let's imagine that we just joined the data engineering team of a new hot video streaming on demand service called Sushi Flix, which exclusively serves content in which people eat sushi. It's fairly niche, but quickly gaining in popularity. So we've been tasked with finding new, better ways to measure performance of the titles on our service. So we open SQLMesh UI, which is also completely free and open source, and we navigate, using search, we navigate to a title performance model. And unfortunately, it's not clearly seen, but at the bottom we can see the full data lineage of this model, including column level lineage. And we can see that the data comes from the playbacks dataset, and it feeds into top titles, which we can assume subsequently used in some sort of a report or a dashboard. So the model definition itself tells us that this is an incremental model which runs daily and consumes playback records in chunks, and those chunks are 1 day long. Now we have a couple of metrics here, and let's imagine that we have a hypothesis that a better metric would be not just a ratio of people who finished the title, but also liked it, explicitly pressed a thumbs up button in the app. So we're going to make a change, but before that, we need a development environment or testing environment. So I'm going to click on the environment drop-down at the top and create a new environment, and we're going to call it dev. So after that, we're going to make a change. We're going to add a new projection with a new metric definition. And SQLMesh immediately identified that we just directly modified title performance model. In addition to that, there is an indirect modification, indirect impact of our change that impacts top titles model. Now, all changes in SQLMesh are applied through the plan command. So if you're familiar with Terraform, this flow was heavily inspired by Terraform. So if we click on the green plan button at the top, we are presented with a preview of our changes. No computation taking place yet. Instead, SQLMesh provides us like a detailed overview of what about to happen. And here we see that SQLMesh already identified our change as non-breaking. We can expand our change and see a diff of what has changed, as well as change the categories that SQLMesh assigned if we happen to disagree with it. So in this case, we do agree with it. So we're going to proceed and check what SQLMesh is planning to evaluate or execute, or using SQLMesh terms, backfill. So basically, what data will be materialized. And in here, we see that only one model needs to be computed, which is the title performance, which we directly impacted, and nothing else, because the new projections that we added has no impact whatsoever on top titles, because it's not used there yet. Also note that we don't need to recompute playbacks. We just reuse the data that is already there in order to compute the new version of title performance. So we're going to go ahead and apply the plan. And while working on this task, we realize that we see a lot of garbage playback session in the data. And by garbage, I mean they are all 0 duration, 0 millisecond duration. Maybe there is some issue on the reporting side. Maybe something else happened, but we know that it's a lot of noise, and it negatively impacts our finished ratio. So we have a new hypothesis. Instead of adding a new metric, let's modify the existing metric and filter out 0 duration sessions. So now SQLMesh again identified a directly modified change, but this time when we run plan and preview our changes, the change was categorized as breaking, because this metric is directly used in the title performance model. So now, if we look at what SQLMesh suggests us to evaluate, we see 2 models instead of 1. So both title performance and top titles needs to be computed in order to correctly preview and correctly reflect our changes. So we're going to go ahead and apply the change. OK, results are good. The new metric definition is much better than it used to be. We now have a lot better signal than before. So we are ready to deploy a change back to production. So we're going to click the drop-down environment again. We're going to pick prod, and we're going to run plan again. Again, SQLMesh identified a breaking change, but here is a striking difference. There is nothing to evaluate. There is nothing to backfill. The reason is SQLMesh knows that this version of the model that you want to promote to prod has already been backfilled in dev, and nothing has changed since then. That means that we can reuse that snapshot table, if you remember the concept from earlier slides, as is, and just like swap the pointers in production. Furthermore, SQLMesh, you probably don't see, but the button at the bottom says apply virtual update. So SQLMesh suggests that like the update that we are about to apply doesn't involve any computation. It's just a metadata change. So it's extremely safe and fast to apply. And we are done. One thing I would like to point out that normally all these manual steps, you are not going to do all these manual steps. This is purely for demonstration purposes. Normally, all the environment creation, plan application, etc., happen automatically as part of the CI/CD process when you, for example, submit a pull request on GitHub, or merge your changes to main. With that, that's all I have. Thank you so much. And please join us Slack to learn more, to meet the team. And yeah, thank you all.